In today's class, we're going to be talking about stream response to water input events. Before we begin with that, just a few reminders. First of all, that the Huntington Sanitary Board project Stage 3 submissions are due online by Thursday, the 31st of October at noon. So please upload them to the appropriate location on MU Online by that time. Also, the homework assignment that goes along with this segment of the course, a hydrograph assignment, will be due on Thursday, the 7th of November. Stream response is important for a variety of reasons, and the first of them is that we rely on the availability of fresh water in streams and rivers and lakes in order to provide drinking water for municipal supplies. And so we want to know how much water there's going to be and when it will be there for reasons related to drinking water availability, industrial water availability, and we've talked about that in a previous class, the importance of there being water and how in West Virginia, for example, that's one of the natural resources that makes the state attractive to incoming industry. Another important reason why we want to know how much water there is and when it will be there is in order to predict and forecast floods. And the text has previously made the distinction between a prediction and a forecasting, and specifically what that is a prediction looks at what the response of a certain return period storm will be, whereas a forecast is looking at a specific actual event and trying to determine in the short term what the conditions are going to be of either maybe a weather event or, in response to that weather event, the stream response. So what is the river going to do over the next week would be an example of a forecast, and what is the river going to do in response to a 5-year storm is an example of a flood prediction. The other reason why it's important for us to study stream response is because water quality is affected by variations in flow rates. And just to give you an idea of that, the photo that's depicted there at the bottom of the screen is showing powdered activated carbon being added to a drinking water treatment facility. And in a lot of agricultural areas where surface runoff contains pesticides and fertilizers, which are dangerous for people and that people shouldn't be consuming, during certain periods of the year when there's a lot of runoff, and particularly when there are heavy rains that may wash the pesticides and nutrients off of the soil and into streams, treatment plants have to add this powdered activated carbon into the treatment train in order to absorb and remove those organic pollutants. And so having an understanding of the stream conditions allows us to make better decisions when managing water quality. Previously, we've introduced the definitions of hydrograph and hydrograph, and this is just a reminder of those and a depiction of an actual storm from back in 1973. Each one of these bars on the hydrograph represents 2 hours, and what you can see is a rainfall rate in increments of 2 hours during the course of a storm that lasted approximately a day, starting midway through the 17th, going through the 18th. And what you can see is that in this case, the storm started off relatively slow. During the mid-period of the storm, there was an elevated intensity, and then the storm intensity tapered towards the end. Now, when we consider the stream flow hydrograph, which is a representation of the response to that precipitation event, the first thing to observe is that actually there isn't much of a response in the very first 2 hours, the first 4 hours. You can see that it's just a sort of gradual increase in this base flow that was probably the flow conditions before the storm occurred. It takes some time for the stream to respond to the rainfall event, and you can see that the peak of the storm event happens after the peak of the rainfall, that much of these high intense periods of rainfall were prior to the peak runoff. And then, of course, that makes sense. It's not going to have runoff before the peak rainfall, but how far apart these two peaks are depends on a lot of characteristics related to the watershed. There may be a long period of time that the precipitation takes to travel over the surface and finally make its way to a channelized stream and then towards the outlet, and it may be relatively quick, and that depends on slope, roughness of the channel, and a whole host of other factors. So stream response can be characterized by a runoff hydrograph, and oftentimes what we'll do is we'll study the relationship between a hydrograph and a hydrograph for a certain watershed, and we'll come up with a detailed characterization of a response to, for example, 1 inch or 1 millimeter or 1 centimeter of precipitation. And then we'll look at what's the response to a certain size storm and extrapolate from there. The figure that's shown here is just a representation of what happens when there's precipitation over a watershed. And this conceptual diagram of a watershed shows a basin boundary, the elevated region, which is delineating where the surface runoff is going to move. You can see that water enters the soil, and so it enters. Here is the zone of aeration, and below the zone of aeration is the zone of saturation. And because there is a ridge line around the edge of the watershed, that also elevates the water table. The water table won't be entirely horizontal, and so the water table is sloping towards the channel, and that's going to cause flow underground. There's going to be flow through the saturated zone towards this channel, as well as there's going to be flow over the surface and in small tributaries to the main channel. So this is just a basic representation of the flow network and path. Now, an even more conceptual diagram would be here, where you can see there's flow over the surface, sheet flow over the surface, which makes its way into a small stream. And the increasing size of that wedge as it works towards the main channel indicates that as there's more and more surface flow contributing to the channel, then the flow rate is going to be increasing. And the same thing's true of this main channel, that you can see that when there's just one of the tributary channels, the main channel isn't very wide, but when there are two, the main channel is getting wider and progressively wider. And so these lateral inflows are themselves fed by surface flow that is accounting for the response to the precipitation event. There are several different kinds of drainage basins, and the type of drainage basin that you have in any one area is dictated by the topography of that area and a lot of the geographic characteristics. In a dendritic network where there's uniform resistance, that the soil is eroding at a uniform rate, there aren't some parts of soil that are eroding slowly and others that are eroding quickly. It looks like sort of a random pattern, a web of channels that are connected together. And to contrast that, a rectangular drainage basin may exist in areas that have fractured rock or fault lines. That here you can, by contrast, where even the main channel was meandering with seemingly little organization, here the main channels are less meandering and are following more of a straight line, and that could be due to fault lines or to a fracture in the rock that occurs. And trellis patterns are another type of drainage basin that may exist when there's an unequal resistance to erosion, but you can still see that there is a main direction of flow. And so here would be a ridge line where you don't see the stream. What that representing is a high point in the soil or in the land surface. And so there's another ridge line here, and this would be a long, narrow valley that would cause the stream to be flowing towards the outlet in the left. The water pools, and the reason why it's a low point here, this is the valley and this is the hill, is that over the long period, over the geological time, the elevated parts were more resistant to erosion, and this part that's been sort of excavated by the flow of water over the surface was less resistant to erosion. And then another type of trellis in mature coastal plains, there can be patterns that look like this, where it's even more sort of rectangular in the shapes that are formed by the main channels and the tributaries. Stream ordering is a way of analyzing how many upstream channels there are at any point in the stream network. And a first order stream is something that has no branches upstream of it. It is a stream here indicated with the number 1, meaning that there is no channelized flow upstream of it, that all that a first order stream is receiving is flow over the surface of the land. But then here in a second order stream, what you can see is that it's also going to receive flow over the land, and it's going to be receiving flow from only first order segments. And so when you have 2 first order streams coming together, then that would form a second order stream. And you can see that when you have a third order stream, a pair of third order streams coming together, that forms a fourth order stream, and it would become a fifth or sixth order stream when you have a fourth order stream joining something that's of a higher order than that. So this is a way of classifying stream order, and the reason why it's relevant is it can give you a sense for the upstream drainage area. It can give you a sense for how large the channel is going to be during a wet weather event, and how significant a channel is to the movement of water through a watershed. Another thing is that, remember, during a wet weather event, most of these channels may be full of water, but when the weather is dry and there's less flow through the upper reaches of the network, there may continue to be flow through the lower reaches of the network just because of base flow or the movement of groundwater in towards the stream. And in order to classify those different temporal differences of when a stream is flowing and when it's not, there are classifications of perennial streams, which is a stream that's continuously flowing and it has a well-defined channel. It's always going to have water in it, either fed by surface runoff or by base flow. An intermittent stream is something that would only have flow in it during the wet season. And then an ephemeral stream only has flow in it as it's actually raining. And so here in West Virginia, you know, in people's backyards there will typically be an ephemeral stream, but then if you go down the hill there would be an intermittent stream, that the creek that flows you know, most of the time but not always. And then a perennial stream might be, for example, the Guyandotte River or the Mud River, something that's always got continuous flow in it and a well-defined channel. Here's an illustration of a perennial stream. This is the Provo River in Utah that always has water flowing through it, and in fact its flow through this Provo River is regulated by a dam upstream. An intermittent stream has a fairly well-defined channel, but as you can see from the photo here, it's dry at this particular season of the year. And then an ephemeral stream is not particularly well-defined channel. It may just look like a ditch or a low point in the hillside that water will accumulate just only during the times that it's actually raining. In these figures it shows how during dry periods versus wet periods the reach of the stream goes deeper into a watershed. And during a dry period, the thick lines here are showing where water is actually flowing, and so the water is actually flowing only a small period, only a small length, but then this dashed line is representing an intermittent stream, where if it was actually raining, then this would have flow in it. And so here during rain or after extended rainfall, you can see the reach of the stream network goes deeper into the watershed, and those surfaces that are actually seeping groundwater are larger. There's more of them and a larger area of the streams that of the ground surface that's discharging water directly into the stream. Another way of looking at it is that even a very large watershed is going to have smaller segments that you could take a look at on the smaller scale. And there's a figure in the text that's very illuminating to help you understand the response of a hydrograph to a hydrograph. And so here at the top of the figure, it's showing a hypothetical storm where it was beginning to rain a little bit early on, and then there was another pulse of rainfall, and then a little bit later there was some more rainfall. And you can see that these progressively increasing peaks are a direct response to the rainfall response. And so here's a period of rainfall that causes the first peak, and there's some time lag between them. And the same thing is true of the second pulse of rainfall excess, that there's a peak of runoff as a response to that. And it didn't go all the way back down to zero flow rate, and so that tells us that it's taking a bit longer than the period between these rainfall excess pulses to drain the network. And so after the second peak it recedes a little bit, but it's not receded down to zero before the third pulse occurs, and the peak increases even a bit more. And then there isn't any more significant rainfall after that, and so there's a gradual recession of the precipitation, the runoff. Now this was for a small drainage area. This was for a drainage area of 0.2 square miles. And so if we were just looking at a very small part of the watershed, then somehow gauged a small tributary off the side of the watershed, and we were just looking at the rainfall from that. Now if we looked at a little bit larger part of the watershed, so now we're considering an area of 3.2 square miles, what we notice first of all is if you look at the y-axis here, the peak flow rates are getting larger. Here the peak flow rate for the 0.2 square mile drainage area was not quite 20 cubic feet per second. But then here on this axis you can see that the peak is up over 60 cubic feet per second. And so that makes sense because we've got a larger area. Of course there's going to be more runoff. The other thing to notice is that the peaks are further to the right, whereas this first peak was just a little bit to the right of the rainfall excess depicted in the hydrograph. The first peak in the progressively larger drainage area is further to the right, and so there's more travel time involved with the larger drainage area. And the other thing to notice is that because of that larger travel time, it's not receding down as far between peaks, and so it's sort of smoothing out the effect of the peaks, and the attenuation of the peaks is because of the travel time through the larger watershed. And so now here with an even larger watershed, 16.6 square miles, you can see we're looking at a larger area, and we don't have any distinct peaks any longer. They've all sort of bled together because of what a large area we're considering. And then when we consider the entire watershed, an area of 43 square miles, again the peaks are still higher because it's a larger watershed area, but the height of the peak relative to the height of the receding leg of the hydrograph isn't quite as distinct. If you consider the height of this peak relative to the receding leg, there's a big difference. And so this smaller watershed was more flashy, as they say. It's more of a flash flood, whereas in the case of the larger watershed, there's a more gradual and even response to the rainfall. The mechanisms of flow can be broken up into a couple of different categories, including channel precipitation, which is where rainfall comes in contact with the stream directly. And so if it's raining onto the river, then it's very easy to calculate the amount of rainfall excess that there's going to be, or how much runoff there's going to be when it rains onto the river, since the river isn't going to have any losses. All of the water that falls into the river due to rainfall is going to stay in the river. There isn't going to be runoff from the river outside of the river. And so it's very easy to calculate the amount of runoff due to channel precipitation. And there's a diagram in the text that shows that if you know the peak flow rate of the precipitation, then you can find the total amount of precipitation that is going to be inside of the channel by knowing the area of the channel, the amount of channel W, the amount of rainfall, where W would be the intensity times time, and then it takes into account the duration of the rainfall and then the duration of the time of concentration. One thing to point out though, and it's illustrated by this figure, is that it's a relatively small fraction of the actual runoff that there is, or it's a small fraction of what's inside of the channel, because the area of the river relative to the area of the entire watershed is relatively small. In the case of the Greenbrier watershed, which was discussed in a previous class, you'll remember that the Greenbrier watershed is 1,650 square miles, and of that only 0.5 square miles is water area. And so it's easy to calculate, is the good news, the amount of runoff that there will be because of precipitation directly onto the stream. But the bad news is that it's almost insignificant relative to the quantities of runoff that are due to land area and precipitation contact. So of the flow mechanisms, overland flow is far more important than channel precipitation, which is the rainfall directly onto a stream. The text makes the distinction between two different kinds of overland flow, the first of them being Hortonian overland flow. And you can tell from the diagram here that in Hortonian overland flow, which is named for Horton, and you'll remember that we had the Horton model for declining rate of infiltration. Here, what causes overland flow is when the infiltration is less than the precipitation. And so at the beginning of a storm, soil is readily absorbing moisture as there is a thick column of soil that is unsaturated. But as the soil becomes progressively more saturated and the wetting front is deeper down into that soil column, then the rate of infiltration decreases, and eventually, as crosshatched is indicating here, there's going to be flow over the top of the surface because the wetting front is still continuing to move down through the soil, but there is saturation from above. The soil pores are fully saturated, and so when they can't infiltrate as quickly as it's precipitating, then the flow will go over the surface and into the channel. And for a lot of years, Hortonian overland flow was assumed to be the dominant mechanism for flow observed overland flow. But increasingly it's becoming clear that saturation overland flow plays an important role as well. And saturation overland flow is a little bit more complex, and it's harder to model because it takes into account the topography of a watershed. Let's just discuss the basics of what saturation overland flow is. By contrast to Hortonian overland flow, which assumes that the soil is becoming saturated because of flow from above. In other words, the vertical movement of precipitation down through the soil slows, and then there's ponding, and then there's overland flow because of the ponding. Here in saturation overland flow, what it assumes is, yes, there is going to be infiltration, but as the groundwater begins to rise, as the water table gets deeper and deeper, there's going to be a point when the water table is higher than the ground elevation. And so you can see between these two pictures, here is at the beginning, early stages of a storm, and then as the storm has progressed and the water table is getting deeper because of infiltration, it hasn't yet reached the point that the surface can't absorb water anymore. There's still a zone of aeration above the water table, but the water table itself has become deeper to the point where the water table is above the ground elevation, and so now there's some return flow. There's flow over the surface, and so not only is there movement towards the channel because of this what was groundwater coming to the surface and flowing over the land, but now any precipitation that falls in this zone that is experiencing return flow is also going to contribute to the overland flow that's making its way towards the river. We can distinguish what makes its way into the stream as base flow and return flow. Base flow is the groundwater that would be entering the channel even during dry events, whereas return flow is that flow that was illustrated on this slide. It's the flow that when the water table rises because of a wet weather event, the return flow is previously groundwater that re-emerged at the surface and made its way into the channel. And these two diagrams are also illustrating overland flow. Here it's showing that in the case where there's return flow, there will be saturation overland flow. We've talked already today about a hydrograph, and we can break the shape of a hydrograph into pieces and label each one of those parts. It's a graphical representation of stream flow, and you can see here on this diagram it's representing both the hydrograph, and so each one of these bars is indicating that there was a storm that occurred, and we were able to measure the intensity of the storm in 3 distinct periods. It started off slow, then it got higher, and it receded a little bit. So here was the rainfall that caused this runoff hydrograph that we're observing. And the hydrograph itself is broken up into parts. You can see that the first part of it down at the bottom is the base flow. The base flow, remember, is that moisture that is inside of the soil, regardless of whether it's a wet weather event or a dry weather event, that will make its way into the channel. So let's go back and look at the base flow. This is dry weather, and yet the water table is still perched in the high elevation part of the watershed. We're looking at a ridge line over here, and here's a high part in the watershed. And so where there's elevated land, there's going to be an elevated water table, and because the water table isn't horizontal, there will be a horizontal movement of the water towards the stream. And the base flow is that water that would always be getting into the stream, regardless of whether it's dry or wet. What this is illustrating is that there's also interflow, which is the lateral motion of water in the zone of aeration during a wet weather event. And it's the amount of interflow is increasing as the storm goes on, because there's going to be the movement of water through the zone of aeration during a storm event. And then the saturation overland flow, this is the water that is either made it to the channel because it's flowed over the surface because of the saturated overland flow that we've talked about previously, or maybe it's a Hortonian overland flow as well that would be up on top of both interflow and base flow. The hydrograph is, they're labeling here a rising limb as the flow rate is increasing, and the falling limb after the peak where the flow rate is decreasing back down to the original base flow rate. There are a variety of conditions that can have an impact on a hydrograph shape. And you can see here a couple of different watersheds. This is a wadi, as they're called in the Middle East, where they're almost vertical rock cliffs, and when it rains the water will come through very quickly. And here is a mountain, a series of waterfalls in West Virginia. From the text it refers to abstractions, and we'll talk more about abstractions in a future lecture, but what we have to keep in mind is that there won't be overland flow until the surface has been wetted. In a channel, for example, if it's a concrete lined channel, you won't have flow through the channel until the concrete itself is wet. So it takes a certain amount of water just to wet the concrete, or if it's flow over a dirt surface, the dirt has to become wet before there's going to be movement of the water over the surface of the dirt. And the same thing is true of any vegetation or surface, that once those local abstractions or temporary interruptions have been filled up, then there can be a movement over the surface towards the outlet. How much water there's going to be and what the shape of the hydrograph looks like is a function of the drainage area, and we've already looked at how drainage area had a big impact on the hydrograph shape, and it was a larger drainage area was attenuating the peaks. Although the peaks were larger, they weren't quite as flashy as it was for the smaller area. Channel slope can be an important contributor to what the hydrograph looks like, because a steeper slope will allow the water to move through the watershed more quickly. Hydraulic roughness of a channel can delay flow, and a very hydraulically rough channel will provide more routing and more attenuation and will slow down the flow as it moves towards the outlet. There can be other factors as well, like the amount of storage inside of a channel, or if there are puddles and ponds along the way, as well as the stream length and the shape of the stream. Other factors as well that we'll go through here and take a look at some of the things that can have an effect on the hydrograph shape. And so comparing a relatively gentler slope to a relatively steeper slope, you can see that of course the steeper the slope inside of the watershed, the higher the peak will be. And the reason for that is that a steep slope allows water to be transmitted more quickly. Comparing the effects of hydraulic roughness, you can see that a stream that is more rough is going to have a attenuated peak compared to a relatively smooth channel where the water is able to move more quickly. The peak will be both higher and earlier. The peak is further to the left here compared to the peak being further to the right for the rougher slope. In the case of there being intermediate ponds and puddles and pooling along the way, that storage is going to delay the movement of water towards the outlet, and so there's less of a peak in the case of intermediate storage. In the case of drainage density, where there's a lot of density of drainage available, meaning there's a lot of channels, that it's not just one main channel and there has to be a lot of overland flow towards it before it gets to the channel. In a network that has lots of channels and you're never very far from a stream, then the water can collect more quickly towards the outlet, and we have a higher peak and an earlier peak than in the case when the water is forced to flow over the land, because flow over land is slow compared to flow through a channel. Channelized flow is always going to be quicker than overland flow. Another instance will be channel length, and this one's just self-explanatory, that if you have channels that are relatively short, then the water doesn't have to travel as long between point to point, and during the travel time the peak is being attenuated because of forward movement and the delays of a peak as it's moving downstream. The routing delays sort of spreads out a peak, and so longer stream lengths will have lower peaks. Another important thing is look at the difference between when it rains in a storm. Even if it's the same total amount of rain, if it rains early in the storm, then obviously you're going to have the peak earlier than if the bulk of the precipitation occurs later in a certain period. And here the peak is later during the storm event, and so there was a gradual increasing flow rate and then a quick recession. Another interesting thing to consider is what happens if the storm is just over part of a watershed versus all of the watershed. Here in the case where storm A is at the furthest reaches of the watershed, very far away from the outlet, the water that falls here at the edges of the watershed must first flow overland before it finally gets into one of these secondary channels and then works its way towards the primary channel and then exits at the outlet. And so there's travel time inside of the channel and over the land. Whereas when it was raining everywhere in the entire watershed, then the water that falls here is already close to the outlet, and so you're going to see a much quicker response. You can see here the watershed hydrograph is larger for storm B more quickly, but then the other thing is it's not just because it's closer to the outlet, but it's sort of lubricating the path. This channel is going to have water in it more quickly, and so the amount of water that fell here is going to make its way through the network more quickly because all of this water over here had to satisfy the abstractions along the route towards the outlet, whereas the water that falls in that same area in storm situation B, the channel has been wetted by flow that arrived there before it, and so you'll see a much larger peak and an earlier peak in the case of a spatial distribution that's all over the watershed boundaries. It's another interesting thing to consider is what's the effect of a storm that is moving from the outlet towards the furthest reaches of the watershed. So what if the storm is moving away from the outlet? In the case of A to B, you can see that the hydrograph peak comes quickly. But in the case of movement towards the outlet, it takes longer for the peak to occur, but it's a larger peak. And the reason for that is that it's sort of raining on top of that wave of high flow as it's working its way towards the outlet. And so the rain cloud is following the water as it travels through the watershed. And so it's sort of raining on top of where it's already wet. That's why the peak is higher, although it is delayed. We've been talking about precipitation and rainfall, and it's important to distinguish between rainfall and rainfall excess. And the difference between the two is the abstractions having been satisfied. And if there's a certain amount of rainfall, and you can see here from the diagram we have a rainfall hydrograph. If you subtract the amount of rainfall that's lost due to infiltration, then what's above that line of infiltration is referred to as rainfall excess. It's going to be the actual amount of rainfall that's available for runoff after satisfying infiltration, and sometimes it's also taking into account the wetting of surfaces that I've previously referred to as abstraction. Of course, we know from our previous work that infiltration is decreasing over time because the forces that drive infiltration are declining. As the soil is becoming progressively more saturated, there's less of a driving force causing elevated infiltration rate. We've characterized the difference between a hydrograph and a hydrograph. Here what we're looking at so far is just the hydrograph of the rainfall excess. But we can get a hydrograph by connecting the dots. This is a conceptual diagram, a flow chart that shows how you go from getting some amount of rainfall that there was and getting a runoff hydrograph out of that. The first step is to quantify and characterize the input rainfall. We'll subtract the abstractions, whether they're infiltration or the wetting of surfaces or maybe interception by plants or interception by buildings. And the moisture that's over and above those abstraction demands is the rainfall excess. You can put the rainfall excess amount into what's called a unit hydrograph. We'll work a unit hydrograph example here in a moment, but the unit hydrograph is that typical shape of runoff that we can extrapolate based on once we've developed a unit hydrograph for a certain watershed. And then accounting for base flow is knowing that there was runoff in the stream even before the rainfall event began. And so you can see that this hydrograph has been boosted up above. It's been elevated a certain amount to account for the base flow that's always in the stream regardless of whether this most recent rainfall event has occurred. So here's a little bit more information about a unit hydrograph. Let's say, for instance, that we had 1 unit of rainfall, whether it's an inch, a centimeter, or whatever. It's a certain amount of rainfall that occurred, and so here's the hydrograph showing that during a certain time increment there was 1 unit of rainfall. This is the hydrograph in response to that 1 unit of rainfall. If we can say that every time there's a unit of rainfall, the watershed is going to do this, then what we could do is we could say, well, what would happen if there's 2 units of rainfall? What we'd expect is that the hydrograph would be larger. If there's 3 units of rainfall, it would be larger still. And the other thing we can do besides adding additional units of rainfall is we can stagger when they occur. And that'll be illustrated on the next slide. But the basic principle here is that if you know how a watershed responds to one storm, then you can predict how that watershed is going to respond to other storms as well. There are some assumptions here that are important to identify because they limit the applicability of unit hydrographs. The first is that you assume there's going to be constant intensity of rainfall during the period in question. So it may be a 1-hour period and you assume that a unit of rainfall occurs, that there's a steady intensity during that period. And what we know is, of course, there isn't any period of time that the rainfall is perfectly constant, but we have to assume that as a simplifying measure. The other thing is that we'll assume when we're applying unit hydrographs that the same amount of rainfall occurs everywhere in the watershed. And that can be a little bit tricky. We want to try and limit the use of unit hydrographs to relatively small watersheds because it's progressively more and more unlikely if you have a super large watershed to assume that the same amount of rainfall occurred everywhere in that watershed. So we have to apply this judiciously to relatively small watersheds to get accurate results. The other assumption we make is that the watershed itself isn't changing over time, that you couldn't develop a unit hydrograph back in the 1960s and then 40 or 50 years later, after a lot of development has occurred, assume that there will be the same response. If there's more and more impervious area, or if there's been deforestation in an area, then the watershed is going to respond differently to that. You can combine multiple unit hydrographs together. So let's consider the case of what if we know that it's raining, there's a certain number of rainfall amounts that we're going to label P. That's the rainfall excess. That is the precipitation after having satisfied the abstractions. And we're going to use the unit hydrograph in order to find the Q, which is the runoff response to the pulses of rainfall that occur. Here's an illustration that shows if you begin with the unit hydrograph, which was just some typical shape, then you can see that U1, U2, U3, U4, U5, that's the response of the first amount of rainfall that occurred. But then we're going to say it also rains during the second hour. It's not just a 1-hour rainstorm. We're going to say it rains during the first hour, but it also rains during the second hour and during the third hour, and we're going to combine runoff hydrographs together. And this is just sort of a conceptual representation of the example that we'll work here in just a moment that shows how to combine unit hydrographs together. So now here in this example, we're going to consider the situation where here's our unit hydrograph. If there is 1 inch of rainfall excess, this is what the watershed does. The rainfall excess falls between 0 and 1 hour. So from hour 0 to hour 1, there's an inch of rainfall excess. And at hour 0, there's no flow rate. But then at hour 1, which is right at the instant, at the hour 1 is when it stops raining, then we're going to measure 10 CFS from our watershed. And then at hour 2, 100 CFS from the watershed, and so on. So this is just from that 1 inch of rainfall excess. And the reason why it's taking a long time for all of that water to get towards the outlet. Why are we still seeing flow at hour 5 when it stopped raining at the end of hour 1? Well, it's because it takes time for water to flow through the watershed. So here is our unit hydrograph. What we're going to do in this example is we're going to say, what if it rained 0.5 inches during hour 1, during hour 2 it rained 1 inch, during hour 3 1.5 inch, and so on. Now these are the precipitation depths, and what we have to do is reduce the precipitation amount by the rainfall abstraction depth, and so there's 0.3 inches of precipitation. Then we're going to find the rainfall excess as 0.5 inches of precipitation minus 0.3 for the abstraction, and so the rainfall excess amount is actually going to be 0.2 inches during increment 1. It'll be 0.7 inches of rainfall excess during hour 2, 1.2 inches of rainfall excess during hour 3, and so on. So what I'd like you to do is go ahead and start up Excel, and we're going to work through this example together. I'd like you to type these same values into Excel as I go through it so that we can get a sense for how to use a unit hydrograph. Just to reiterate what the unit hydrograph means, if there is a unit of rainfall during the first hour, so between 0 and 1 there is a unit of rainfall, this is the response we're going to see. What that means is that during the first hour, flow from this region is contributed to the outlet. During the second hour, it's flow from this region, region 2, that's made its way towards the outlet. During the third hour, this region contributes to the outlet, and so on. So you can see by hour 6, it's the flow that's finally at the furthest part of the watershed that's finally made its way towards the outlet through either overland flow or finally getting into the channel. Now, this is the response to 1 hour of rainfall, and it's a 1 inch during 1 hour. What we're saying in this example is that we have 0.5 inches of precipitation during the first hour, then 1 inch of precipitation during the second, and so on. And we're going to have to find what's the rainfall excess that's left over during the precipitation event, taking into account the abstractions, and then send each one of the hours through this unit hydrograph shape. And that's the procedure we're going to pass through in the example that's going to be demonstrated using Excel now. So let me go ahead and start up a copy of Excel, and first copy the information from the unit hydrograph into Excel. Here's the unit hydrograph. And then we have the rainfall response. Okay. What we need to do is take into account the fact that there are abstractions. And so there's a precipitation of 0.5 inches, for example, during the first hour. Abstractions are 0.2 inches of rain during each of the hours, and that was defined, 0.3 inches defined in the problem statement. And that's a constant through each of the hours of rainfall. And so then rainfall excess is simply going to be the difference between the two. I think I must have typed that in wrong. So it is, there we go, that's making more sense. So this is how much rainfall is actually available to work its way towards the outlet. And the unit hydrograph is how much runoff there was due to 1 inch of rainfall excess. Okay. What I'm going to do now is just copy these hours, and probably we're going to need to extend that time period beyond the 6-hour increment, and I'll show you why in just a minute. Let me just go through like that. So what's going to happen during the first hour? Well, during the first hour there is 0.2 inches of rainfall excess, and so hour 1 will be this amount, and I'm anchoring that by pressing the F4 key, times this. So if there was 1 inch of rainfall excess, there would have been 10 CFS. But since there's only 1/5 of that, then the response is 2 CFS. So 2 out of 10 is the same as the 0.2 inches of rainfall versus the 1 inch of rainfall excess that caused the unit hydrograph. So I can copy this down and see that the response is scaled. The response is scaled, and now during the next hour we have to shift it down though, because it's starting during hour 2. And so once again we're having the same rainfall excess amount, and I'm anchoring that by pressing F4 times the unit hydrograph. And so for 7/10 an inch, where the unit hydrograph would be 10 CFS, we now have 7 CFS. That makes good sense. And then you can see that hour 1 response is here in hour 2, and the reason why we've staggered it down is that it goes through the whole cycle of the unit hydrograph, but the cycle is staggered because it's this pulse of rainfall happened during the time from hour 1 until hour 2. And this pulse of rainfall was from hour 0 to hour 1. So I'm going to drag this down, and that tells me what the response is to the second pulse of rainfall, and so on. The rainfall that went during hour 3, I'm going to have here on line hour 3, and it will be the rainfall excess amount times the unit hydrograph, and I can just click in the corner here and it will drag it down. I don't want it to continue that far though. And finally the 4th hour. And dragging it down. And then the total will be the sum of all of these. So it's the sum of every column to the left, except for the hour, the sum of the flow rates. And what we're talking about is the total, and this is units of CFS. And so, for example, during hour 4, lots of things are happening during hour 4. The rainfall that occurred during the first increment of time is finally made its way towards the outlet. The rainfall that was here has finally made its way towards the outlet during hour 4. You can see that each one of the contributing areas gradually makes its way towards the outlet, and at any one time there may be more than one contributing area that's feeding towards the outlet. And that's how we interpret this unit hydrograph figure. What the meaning of this figure, which we looked at previously, is that, for example, during the first increment where we have runoff going towards the outlet, it's only the area 1 that's contributing. But now you can see in the second time increment, it's area 2, or the response of U2, which is referring to the amount of rainfall that is in the second area, and it's the precipitation depth of the first time increment, and so on. And so using this approach, we can see that this is a schematic representation of the spreadsheet that we just put together. There's a staggering effect where the unit hydrograph is progressively making its way a little bit further down the spreadsheet because each time we move over in a column, we're taking the response of the unit hydrograph and taking it lower because, for example, here this was time 2, the second hour. It's just sort of like we're trying to break the event up into discrete pieces of area, and also the segments of rainfall amounts. So that's the process of applying a unit hydrograph.